Welcome to the Deep Dive. We're the place where we take, really dense research and just boil it down to the insights you actually need. Today, we're jumping right into the core engine of modern AI, large language models. We all use them, right? But here's the thing. They're fundamentally inefficient, deeply so.
That's exactly right. It's baked into their design, this static depth regime.
Wow.
Doesn't matter if you have something super simple like what's the capital of France, or a really complex multi-step math problem. The model just grinds every single token through all its layers, maybe 60, maybe 90 layers.
Yeah.
It's often a huge waste of computation for the easy stuff.
Yeah, it's like having this rigid company rule that every single piece of paper, even a sticky note, has to go through like 3 VPs and the CEO. Total overkill. So our mission today is to really dive into a framework trying to fix this. It's called Dr.LLM. That stands for Dynamic Routing of Layers for LLMs.
And the goal of Dr.LLM is, at its heart, pretty simple. Break that static depth problem. Let's allocate compute dynamically. We want the LLM faster, obviously, but what's really fascinating, what the research shows, is that it often manages these efficiency gains without hurting accuracy. Sometimes it even improves it, which is, really unusual for efficiency methods. Usually there's a trade-off.
Okay, that's the hook. So how does it work? This is where it gets really interesting, right? Instead of this fixed path, Dr. LLM gives each layer a kind of intelligence. It gets to decide what to do. It can skip its transformer block completely, saving compute. It can execute it once, which is, the normal way. Or, and this is key, it can even repeat its block, basically doubling down if the input seems tricky.
Okay, let's dig into that static problem just a bit more. We mentioned the waste on easy prompts. But the flip side is that for really hard stuff, like complex reasoning or math, this fixed depth means the model doesn't get enough, let's say, thinking time. Exactly. It kind of runs out of steam just when things get complicated. People have tried to fix this before, of course. Things like early exit strategies, where the model bails out early if it thinks it has the answer,
Yeah.
or layer pruning, just cutting parts out.
Right.
But those methods, they almost always hit that wall. They needed big architectural changes or complicated search during inference, which slows things down again. And often, they sacrificed accuracy for speed. They didn't quite nail it.
So Dr. LLM comes in with this dynamic solution, and you mentioned it's retrofittable, which sounds really important.
Absolutely key.
Yeah.
They take a frozen, pre-trained LLM, meaning they don't mess with the core model weights, the billions of parameters that cost a fortune to train. They just attach a lightweight router to each layer.
A router. Okay, what does that do?
This router is the brain of the operation for that layer. It's a small neural network, just a simple MLP, multi-layer perceptron, tiny, really. And its whole job is to look at the current state and decide. Skip, execute, or repeat.
So the big, expensive base model stays untouched. That makes it practical, right? No massive retraining needed.
Precisely. That's a huge advantage for actually deploying something like this.
Okay, wait, I need to push back a little here, just thinking practically. If you add a decision step at every layer, doesn't that router itself add some delay, some latency?
That's a fair question, a really important one. But the analysis shows the router is so computationally light, think, maybe 0.14% of the base model's parameters for a 3 billion parameter model, that its overhead is, negligible compared to the savings you get from skipping entire transformer blocks.
Got it. So the savings dwarf the cost. Makes sense. So the retrofitting is great, avoids retraining. But if the base model is frozen and you can't do costly searches during inference, how do you teach these little routers what the right path is? You need some kind of perfect example path, right?
Exactly. And that leads us to the secret sauce, how they train these routers. This is where Dr. LLM sidesteps the problems of older methods that relied on that slow inference time search. Dr. LLM uses explicit supervision, but it's all generated offline ahead of time.
Offline supervision. Okay, and how do they generate that?
They use a technique, pretty classic in AI, actually, Monte Carlo Tree Search, or MCTS.
Ah, MCTS.
Right.
Used in game playing AI like AlphaGo.
The very same principle. They use MCTS offline, just once, to figure out the best paths. So for a given input, MCTS explores tons of possible execution paths, all the combinations of skips and repeats it could possibly take within a certain compute budget. But here's the crucial part. MCTS only keeps the paths that preserve or actually improve accuracy compared to just running the full normal model.
So it's like finding the absolute shortest route on a map that still gets you to the destination perfectly, maybe even slightly better.
Perfect analogy. It hunts for those optimal efficient paths.
And MCTS does all that heavy lifting offline. What's the output look like? Is it a huge data set?
Actually, no. That's another amazing part. The output is this compact, really high-quality data set. Get this. They only used around 4,000 optimized paths to train the routers for all the models they tested.
4,000. That seems tiny for training something related to these massive
It's
LLMs.
incredibly efficient. Remember, you're only training the tiny router parameters, not the giant base model. Training takes just a few hours on a single GPU, like an A100. The base LLM, the 8 billion parameter beast, just sits there, frozen.
Okay, that's impressive efficiency. But training even a small router has challenges, right? Like, what about really long inputs? Or the fact that most of the time the best action is probably just execute? How did they make the router robust?
Good points. They tackled two main engineering hurdles there. First, long contexts. If you just average the state across, say, thousands of tokens, that average becomes really blurry, too generic for the router to make a smart decision based on recent information.
Right, it loses the specifics. So what did they do?
They use something called windowed mean pooling. Instead of averaging everything, the router looks at a summary calculated over smaller sliding windows of tokens, maybe 8 tokens at a time. This gives the router a much more localized, relevant signal about what just happened. The ablation studies showed this was critical. Averaging everything just didn't work well.
Okay, windowing makes sense, keep it local. Now, what about that imbalance? Skip and repeat being rare compared to execute.
Yeah, that's a classic machine learning problem. If 95% of the time the right answer is execute, a simple training loss would just let the model predict execute all the time and get 95% accuracy, ignoring the important rare cases.
Like a student acing multiple choice by always picking C, but failing the essays entirely.
Exactly. So they use focal loss along with some class balancing. Focal loss basically tells the model, hey, stop paying so much attention to the easy execute examples you're already getting right. Focus on learning these tricky, rare skip and repeat decisions.
Mm-hmm.
And again, the tests showed this was essential. Standard loss functions just couldn't learn those minority actions effectively.
Wow. Okay, so some clever engineering there. And there was one more insight about what the router learns, right? It's not just looking at the input question.
That's a really crucial finding. The router learns to map the internal model state, basically, what the previous layer just produced to its decision. They tested a simpler version where the router only looked at the initial input, like, is this a math question?
Yeah.
That performed terribly, even worse than the original static model.
So the router needs to understand the flow of information inside the model, not just the starting point.
Precisely. It's reacting dynamically to how the processing is going. Is the information well-formed? Does it need more work? We cut it short here. It's much smarter than just a simple input classifier.
All right, let's talk results, because that's where the rubber meets the road. They tested this on reasoning tasks, right? ARC for logic, DART for math. Did it actually deliver on both speed and accuracy?
It really did. Across all the models they tested various lemmas, Quinn models' accuracy went up while compute went down, every single time for these in-domain tasks. On average, they saw about a plus 2.25 percentage point gain in accuracy while using 5.0 fewer layers per query. That's a significant improvement on both fronts.
Give us a standout example, one that really shows that dual benefit.
Okay, take a Llama 8B instruct on the Dart math benchmark. Accuracy jumped by plus 2.8 percentage points. That's a solid improvement on a tough task. And at the same time, it used, on average, 11 fewer layers per query. 11 layers. That's a massive efficiency gain alongside better performance.
Wow. Better answers, much faster. That really is hitting the sweet spot. Okay, but that was on tasks similar to what the routers were trained on. How did it generalize? Did the strategy fall apart on totally different out-of-domain ODE tasks?
That's the next big test, right? And the generalization was surprisingly strong. They threw a whole battery of diverse ODE benchmarks at it. Things like MMLU for general knowledge, GSMAK for different math problems, truthful QA, 8 benchmarks in total. And the routers kept saving compute, kept being efficient. The average accuracy drop across all those diverse tasks was only about 0.85 percentage points.
Only 0.85% drop. That's pretty minimal, especially considering the efficiency gains are maintained.
Exactly. It suggests the routing policies learned are quite robust and capture something fundamental about efficient processing, not just specific task tricks.
How does this stack up against those earlier attempts at dynamic routing you mentioned?
Oh, it blows them out of the water, according to the paper. Dr.LLM outperformed prior methods by up to plus 7.7 percentage points in accuracy. That's a huge gap. And think about the training data difference again. Dr.LLM used just 4,000 examples derived from MCTS. One competitor they mentioned, Flexidef, needed something like 326,000 examples and still saw significant accuracy drops on some tasks, like over 6 points down on GSM-8K. Dr. LLM gets better results with way, way less training overhead.
So better performance, better generalization, vastly more efficient training. That's compelling. And this research didn't just build a better system, it also gave us a peek inside the LLM's thought process, didn't it? By looking at where the skips and repeats happen.
Yeah, that was another fascinating part. The learned routing policies weren't random at all. They showed clear, structured patterns across the model's depth. These patterns lined up almost perfectly with how we think transformers work. Initial processing, then feature extraction, then final refinement.
So the model learned to manage its own workflow. Like, okay, need all hands on deck for the start, can probably skim through the middle reports, but needs senior review at the end.
That's a great way to put it. They basically saw three zones. First, the early layers. These were almost always executed, very little skipping. You need that solid foundation, that initial understanding of the input.
Makes sense.
Second, the middle layers. This is where most of the skipping happened. The highest variation. The model figures out, okay, I've got the main features. Maybe I don't need all these intermediate steps for this particular input. It finds redundancy and saves compute.
Cutting out the busy work.
Exactly. And third, the late layers. These were often repeated, especially for those tough Dart math problems.
So when it hits a snag, a complex calculation or logical step, it instinctively gives itself more processing time right near the end, like double checking its work.
Precisely. It allocates extra computation strategically for iterative refinement when the task demands it. It's not just skipping, it's also adding depth intelligently. These patterns show it's not just arbitrary efficiency, it's a learned structural adaptation of the computation flow. It's quite interpretable.
Okay, this has been a really insightful look. Dr. LLM seems like a genuinely practical, robust way to tackle that core efficiency versus accuracy trade-off in LLMs. Using this supervised dynamic routing on frozen models seems like a real win.
It really does. And there's one final piece, a sort of bonus insight that points towards the future. The framework allows for fine-grained control over that trade-off after training. They found they could use a single scalar parameter, like a knob or a slider. Turning this knob lets you smoothly move between being very aggressive with skipping, maximum speed, maybe slightly lower accuracy, and encouraging more repeats, maximum accuracy, less speed saving, all without retraining anything.
A dial. So you're saying in the future, maybe we don't just deploy one fixed version of an LLM. Instead, we could have a sort of budget dial. We could tweak it based on how fast we need the answer right now versus how absolutely perfect it needs to be, making the LLM's resource use fluid.
That's exactly the provocative thought it leaves us with. Are we moving away from static models towards these more fluid, budget-aware intelligence systems? Maybe the LLM of the future doesn't just give you the answer, but also says, okay, I used 55 layers for that hard query because you set the quality dial high, but only 20 for the simple one before it to meet your latency target. It becomes adaptive, not just in processing, but in its resource contract with us.